All right, so we're going to prove, what are we proving now? So we're proving that, yeah, so we're proving the vanishing theorem. Uh, so I want to show that, so here's the theorem. Okay, it says that pi I of Sn, and then, okay, so here we're viewing Sn as Rn plus a mark plus infinity. So this is like, so here, recall that we're really viewing Sn as like Rn union infinity. Okay, so this is going to be equal to 1 for I less than or equal to n, and if n is greater than or equal to 2. Right, so this is what we want to prove. We want to prove that these homotopy groups are vanishing. You don't even need to know what the definition of a homotopy group is. I'm going to show that all the loops are contractible, or all the classes are contractible. Okay, so like the baby case, which is really the proof in the main case, is we're going to prove that pi 1 of Sn infinity is equal to 1 for n greater than or equal to 2. All right. So this is the main case that we want to show, and then this will actually be the base case for an inductive proof here. All right. So what's the proof? So the proof is we're going to show that every loop is contractible. So here's the proof. Okay. So what we're going to do is so let gamma be a map from S1 to Sn. And let's say it's a pointed map. Okay? So if gamma is not surjective, so that would be crazy, right? So so this would be like your curve is going all over the place, which seems highly unlikely. Okay, so later we're going to prove that all of them are not surjective. Then gamma, then we have a factorization. Gamma factors through. So then we have something like this: S1, and then we have Sn minus some point, and then this goes into Sn, and it goes like this. And then this thing here is homotopy equivalent to Rn, which is contractible. Right? Okay, so then if you have your map gamma and it factors through this way, then we can put it in here and just shrink it, right? And so this implies that gamma is homotopy equivalent to a constant map. And since this was shown for all gammas, so this implies that pi 1 Sn infinity is equal to 1. Okay, so that's the idea. So it remains to show that that no such map is surjective. So we need to prove non-surjectivity. That's the hard part. Okay, so here's the proof of non-surjectivity. Okay, so what we'll do is what we'll show that so we'll fix a point, and then we'll show that we can modify the curve to something homotopic to it that doesn't pass through that point. So fix p and S infinity. Okay, and so we will modify and we'll fix gamma from S1 to Sn, right? And so we will modify gamma to some gamma tilde, which doesn't pass through P. Okay, and so here's the picture. So we'll have some point here P, and then potentially we have gamma coming through here like this, okay? And what we'll do is we'll take a neighborhood around P. So this will be B. So B is a neighborhood of P. So, and then and then what happens is that okay, so maybe we can so what we'll do is we will just make this gamma tilde. So if this is going this way, right? So then this gamma tilde just goes around the neighborhood, okay? And then it'll be homotopic to this thing because this disk here is contractible, right? So then all these things will be. So I guess I could have put it inside here as well, but this is the idea. It's just like we go around, okay? But now we need to check out that this is actually possible, okay? So all right. So why is this possible? Okay. So so B is an open neighborhood, and so by continuity, okay. So maybe this is a trick, right? Is that a map from S1? Okay, so a map from S1 to X is the same thing as a map from I to X, where where D of I here, this thing collapses to some point. Okay, so yeah, so that's well, I mean, that's maybe not so crazy. It's so you have, or maybe I can write it as gamma. So really, we just need gamma 0 is equal to gamma of 1. That's all I'm saying is just I'm just parametrizing the circle by this thing. Okay, so we have this correspondence between these two things, and so I'm going to use this picture here, and so I'm going to view this as an interval, and so so by continuity, so okay, so now I'm going to check everything. So continuity tells us that the inverse image of an open set is open. So gamma is a continuous map, and so gamma inverse of this neighborhood is a union of some intervals, AI, BI. Maybe I'll start doing the French thing. Okay, for I and I. Okay, so this is true. So this thing here is compact, right? So we can find a finite subcover of the inverse image of this point. So this means that so there's only going to be a finite number of times, right, that it'll swipe through. So here, we could have our ball here and we have our point here, right? And the thing that we could be concerned about is that it goes through and goes through and then goes through again, but it goes around. So this is gamma, but this can only happen finitely many times, right? Many passes. And in particular, we know that it enters the neighborhood finitely many times. So this is compact. So this means that this thing here is in a finite collection here. I is equal to 1 up to n of these intervals. Okay, that's open interval notation. Because I don't know, I'm writing it like that right now. Okay, and so what we'll do is we define. We define our new path, right? Gamma tilde of t. So this is going to be, well, gamma of t. If t is not in, let's call this t. Okay. And so, and then we'll define this, and then we'll define it to be the path along the boundary. Along the boundary. The boundary if t is an element of t. Okay, so it's going to do exactly like we had in this picture here, except I'm going to draw it exactly on the boundary, right? So this is maybe gamma of like AI, and this is gamma of bi here, this point and this point. All right, and so we have this new path, and since b is contractible, we have that these two things are the same. They're homotopy equivalent, and now we've shown we've produced a path homotopy equivalent to our original one that is not surjective. Okay, so this is a new path. So new homotopy equivalent path, not passing through the b of our choice, or the p of our choice. All right, so that's the proof, right? So we just take our path and then we modify it. If it's not surjective, we remove a point and then we contract. All right. So the proof of the theorem, okay, the proof of the general theorem is exactly the same. All right. So so again, the trick is so again we need to show non-surjectivity. So non-surjectivity suffices of these paths gamma of some gamma tilde equivalent to gamma suffices. All right. So the trick again is a map here from a map from Si to Sn. So so this thing is the same thing as a map from II to Sn, where dii, this whole thing maps to a point. Okay, so we can take this loop here, or we can take an interval. All right, and so so we choose our p. So we choose or let's say, so take gamma to be arbitrary. So let p be an element of Sn, okay, as before, and then we're going to modify this gamma to make it not pass through p. So what we'll do is we take gamma inverse of b, right? So again, so then we let b be here in be an open neighborhood. Open neighborhood. Okay, and we're going to view it as a subset of Rn. Okay, so so what we'll do is we'll take gamma inverse of b, and so it's a union of a bunch of squares, right? It's a union of a bunch of rectangles. It's covered by rectangles, I and j, and then we have I dimensional. Oh, let's see, j and j. I dimensional intervals. Oh man, I really didn't choose good notation here. Okay, so but this is the analog of the intervals. Okay, so this is little pieces like this. Okay, this is instead of intervals we got little squares inside I to the n. So maybe I'll draw the two-dimensional picture, right? And then we got a bunch of squares in here. Okay. So we break it up into squares, and that's what's going to happen. Okay, and so so by compactness, right, we still have a finite subcover. We get a finite subcover, right? And so for p, right? So gamma inverse of p is going to be contained in. So the union from j is equal to 1 up to some finite n of I, these intervals of dimension I. Okay, so those cubes or rectangles or whatever. Okay, and so what we'll do is we just modify, we take a path on the boundary. Okay, so so then gamma tilde. So we define gamma tilde. Okay, and we'll call this T again. Gamma tilde of T. So this is going to be, well, gamma of T, if T is not in T. And then we'll just do a path along the boundary. Boundary of B, if T is an element of T. Okay, and since here this is homotopic to this, and this so this is gamma tilde omits does not map to P. We win. Okay, so that's the proof of surjectivity. All right. Oh, sorry, not non-surjectivity. And what do we prove again? So we proved that these fundamental groups vanish. These higher homotopy groups vanish for we did that by showing that they were all the loops are contractible. Okay.